So this picture might be recognizable to those of you who were born, I think, before 1980. So anybody recognize what game this is? Pong, exactly. So why am I showing this picture of Pong? Pong played an unexpected role in shaping my thinking about autism. So many years ago, over a decade ago, when I knew very little about autism, I still know very little about autism, but at that time it was vanishingly small. Um, we had the opportunity to work with children who were on the spectrum, and we happened to have an eye tracker with us. This was in India. Uh, we were tracking the eye movements of children in Project Prakash that John had mentioned, but we also had the opportunity to work with children on the spectrum, and we had programmed this game, a homebrewed version of Pong. And because we were interested in dynamic information processing, we decided that we will have neurotypical and autistic children play this game while we monitored their eye movements. We didn't really know what to expect, but there were some interesting trends, and I want to start the talk with that background because it's historically significant for me. So here is a neurotypical child playing Pong. They're controlling the paddle that you see on the left with the mouse. This little white square is the ball that will rattle around this three-walled chamber. And while they're doing this, we are tracking their eye movements, and the red tracks are where their eye is looking. So let's view this short one. This, as I said, is a neurotypical child. And what stands out in this short video is how anticipatory the gaze is. So even before the ball gets to a certain point, the child is already looking at that point of contact and is moving the paddle to that anticipated position. Let's compare this to a child with autism playing the same game. What's interesting is that now, instead of anticipating where the ball is going to be, the child keeps following most of the time where the ball has been. So I found this curious, that there was this striking difference between the two groups of children. But I filed it away in the back recesses of my brain. And then, if we fast forward several years, and I began to learn about the complexity of the autism phenotype and how there were many different aspects of behavior that are affected by the condition, the question that occurred to me was, might there be some common threads that link these diagnostic domains of communication, social interactions, and behavior? So are these three foci, do they share any common threads? So to try to make headway on this question, I turned to some of the theorizing that had gone on in each of these domains. So even without reference to autism, many researchers have thought about how best to conceptualize these different domains. These are very short representative lists of the work, the very rich bodies of work that have looked at these domains. And what I was struck by was the formalism that came up again and again across these different domains, across these different pieces of work, was this Markov formalism. To think about these domains as a collection of states, and the behavior of the individual would be transitions from one state to the next with certain probabilities. So the idea is that in order to do well in any one of these domains, what you need to do is, based on your sensory experience, the statistics of the environment that you're gathering, you are estimating these transitional probabilities. And that's what's shown schematically here. You have one state transitioning to another with a certain time gap, And based on a sequence of such observations, you are determining what is the conditional probability of one state following another after a certain time lag. This is the fundamental computation that one needs to perform to estimate what is the model of the environment that one is immersed in. If this computation were to be compromised, then it stands to reason that one's performance in these domains would be significantly affected. And that leads us to the hypothesis that John had mentioned. We call it the PIA, or the predictive impairment in autism hypothesis. So the idea simply is this. If we were to plot, before plotting, so the idea is simply that autism is accompanied by impairments in estimating this conditional probability. So graphically, if you were to plot the strength of the relationship between any two events on the ordinate, and the time separating the occurrence of these two events on the abscissa, then relationships on the lower right are the most difficult to detect, because the strength of the relationship is weak, and one is happening much after the other. The relationships on the upper left are the easiest ones to detect, very strong relationships, and one happens very soon after the other. Some of these difficult relationships are going to be hard to detect, but there is likely a threshold beyond which these relationships become detectable. So schematically, we are saying that perhaps there is this function, which we call the association sensitivity function, inspired by the contrast sensitivity function that has proven so useful in work in vision. So there's some kind of a threshold between the undetectable relationships and the detectable relationships. And according to the PIA hypothesis, autism leads to a shift of this association sensitivity function to the up and left. So that some of the relationships in this region between the two curves, the relationships that are visible or evident to a neurotypical individual become invisible, undetectable to a person with autism. That is the crux of the PIA hypothesis. One important point to note is the concern that if we are saying that all cases of autism, or most cases of autism, subscribe to this idea, then how do we account for the heterogeneity that's so well known about the condition? So one possible way to account for that is that different time regimes on the x-axis correspond to proficiency on different tasks. And depending on where in this time regime the shift happens, you can end up with very different manifestations of the challenge. So for instance, if you have a greater shift towards the left, you might have a person who has more of a language compromise. Here you might have more of a planning compromise, and here you might have more of a broad-based compromise. So we are not saying that all individuals with autism share the same shift. What we are saying is that there is a shift, but the place of the shift might be different, and that might lead to different manifestations. So we tried to capture these ideas in the paper that John had mentioned. We essentially put this down as a hypothesis. We reviewed a lot of the empirical literature that had been accumulated by that point. And we also put forth some of the theoretical arguments behind this hypothesis. But at its core, this was a theory paper. What we have been doing since the publication of this paper is trying to put the theory through its paces. So taking an empirical approach to testing the theory. We are not dogmatic. We are not in such thrall of the theory that we expect it to be absolutely right. It may very well be wrong, and we want to be our own worst critics. So we want to explore, does this theory hold up to experimentation? And we are exploring multiple avenues of experimental work. We are looking at perceptual processing, dynamic interception, and more general probabilistic reasoning. And the reason we are picking these three domains in particular is because they nicely tile the temporal axis. So by seeing whether all of these domains are affected, we would gain some confidence that a predictive impairment, if one exists, is a common thread that links challenges across these multiple domains. So as I said, this project has been very exciting for us because it has allowed us to establish collaborations with wonderful colleagues. So the dynamic interception part, Dagmar will be talking about shortly. And the probabilistic reasoning part is done in collaboration with Nushin Hajikani, who is a professor at Mass General Hospital. She couldn't be here, but I will try to summarize some of that work if time permits. The bottom line for this talk would be that the experimental evidence thus far is not definitive, but it's encouraging. And you will hopefully see some of the reasons why we are encouraged by it. But a lot more work needs to be done in order for us to have more confidence in either accepting or rejecting the PIA. So with that, let me start with the first piece of perceptual processing. So in the domain of perceptual processing, which is of course very rich, there are many different aspects of perception that we could have probed. The one that we have decided to focus on is habituation. How is it that this person on the couch can read even while she's immersed in the sound of the vacuum cleaner? And one reason, or the likely reason, is habituation. After that initial annoyance, she has probably habituated to the sound of the vacuum cleaner. Habituation is a very well-known phenomenon, of course, both in behavior and in neural responses. Your response to a sustained stimulus declines steadily with time. Now, why are we interested in habituation? Because in thinking about the factors that modulate habituation, one of the big ones is predictability. The less predictable a stimulus is, the lower the habituation that it elicits. And there is a lot of experimental evidence that supports this. Here's one particular one. So even at the level of single unit recordings, you find that if an animal is being exposed to unpredictable temporal beeps, you see much lower habituation in the response of a neuron than if it were to be a regular sequence. So if we are positing that predictability, or the ability to predict what's going to happen next, is reduced in autism, then we would predict that habituation also would be reduced in the condition. Is that really the case? So that's the experimental question. It's a very clear experimental target. Is habituation reduced in autism? The way we have approached this question is by presenting individuals different kinds of sequences. Here I'm going to talk about metronomic auditory sequences. So the person is hearing, say, tick, 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 once every second, while we record different kinds of responses from them. So we are looking at the galvanic skin response. In a separate study, we are looking at the neural activity as measured via magnetoencephalography or via electroencephalography. So let's first start with galvanic skin response. With neurotypicals, the data are entirely unsurprising. You see, over time, so the x-axis is time, about 3 minutes, you see a steady decrease in the skin conductance, indicating habituation. So on the top, you see 3 individual subjects, and on the bottom, you see average responses across 18 individuals, and steady habituation across all of them. What happens with autism? So here are 3 individual subjects. So there isn't evidence of habituation. Rather, if anything, it seems like sensitization. If we look at data across multiple subjects, so here's the average across 18 subjects. So consistent with our prediction, there seems to be a significantly lessened habituation in autism. Here, I'm plotting the slopes of the lines of best fit for each of the individual GSR plots. In blue are the neurotypicals, in red are the autistic subjects. And you notice that all of the neurotypical subjects exhibit negative slopes corresponding to habituation. Almost all of the autistic participants exhibit positive or 0 slopes, indicating no habituation. So we were surprised to see this level of consistency across the subjects. And we wanted to look at this a little more closely. So we decided to move to direct analysis of neural data using magnetoencephalography. So the task of the subject is essentially the same. Just sit back and listen to these auditory clicks. And we're recording the neural data across the entire scalp and then looking at responses recorded over the auditory cortex. Now, in an ideal world, with every impulse that you present, you would get an auditory evoked response, and we could compare the response at the beginning of the sequence with the response towards the end of the sequence and see whether there has been a change in the amplitude. A decrease would represent habituation. Of course, real neural data look a lot more noisy, and we have to average a bunch of these individual responses to get the average evoked response. And we can do the same kind of averaging towards the end of the sequence. So you get the average evoked response there. And we can then do the same kind of comparison. Does the average evoked response towards the end differ from that towards the beginning? A reduction in the amplitude would correspond to autism, or would correspond to habituation. So what happens with neurotypical subjects? We see clear signs of habituation. These are 2 individual subjects. The green curves correspond to the first 50 clicks, the evoked response to the first 50, and the red curves correspond to the evoked response to the last 50 clicks. And you notice this reduction in amplitude. With ASD participants, we see an increase in amplitude. And again, if you plot the data across all of the subjects, what you're seeing here is the average amplitude at the beginning of the sequence and the average amplitude towards the end, black versus green. With the neurotypicals, you see that amplitude decreases, whereas with the autistic subjects, you see that amplitude increases. Finally, EEG. So essentially the same paradigm as in MEG. So we are having the person listen to these auditory metronomic sequences, and we are looking at the strength of the evoked potential, and that evoked potential over time is decreasing. For autistic subjects, it's not. And here is the bar plot that you have now become familiar with. So one question that we wanted to ask, is this reduction in habituation that we're observing in autism, is this specific to audition, or is this cross-modal? So if we were to do this experiment in another sensory modality, would we still see this reduction in habituation? So we decided to move to vision, and the experiment is analogous to the auditory one, where instead of presenting clicks, we are now presenting flashes without changing the overall luminance of the display. We are changing these circular checkerboards once every second. And you can do exactly the same kind of analysis to see whether there is this difference in habituation. And indeed, you find that neurotypicals show habituation, ASD participants do not. And here are the individual subjects. We can also merge the auditory habituation results with the visual habituation results to come up with a composite sensory score. And we can now use this composite sensory score to now try to see whether this has any correlation with the clinical scores that we have for these participants. So we looked at scores across a variety of checklists, a variety of clinical instruments, such as the social communication questionnaire and the child behavior checklist. And the interesting observation is that we find a very strong correlation between scores that we're deriving from this purely sensory study with the scores that seem to be a lot more complex and touching upon more complex aspects of behavior. And similarly with the sensory sensitivity profile. So to summarize, GSR, MEG, and EEG data all suggest reduced habituation in autism. There seems to be an interesting point of contact between this result and some work that we are engaged in right now on motor entrainment. So in the entrainment task, we are asking the subjects to tap along to a sequence of sounds that they are hearing. So if you're hearing a metronomic sequence and I ask you to tap on the table in time with the beeps, very quickly you come to be entrained. There is almost a zero lag between the beep and your tap, indicating anticipation. You're not reacting to the sounds, you're actually anticipating the sounds. Do we find a difference there between ASD and neurotypical subjects? And indeed, we do. So in what you're seeing here is the latency between the beeps and the key press. This is a metronomic sequence where the beep is occurring once every 2 seconds. Interestingly, the neurotypicals shown in the blue circles, their latencies are either close to 0 or close to 2 seconds. So they are right in the vicinity of when the beep actually happens, whereas the ASD participants seem to be all over the place. So in this overt motor response, there seems to be evidence of this kind of irregularity in production. And if there is this is an endogenously perceived irregularity, then it stands to reason why we might be seeing the reduction in habituation that we're seeing in our other results. This is just an aggregate result of how many of those entrainment responses from neurotypicals in blue versus ASDs in red, how many of them are close to the actual beep, and they are much more for neurotypicals than for ASDs. But this is ongoing work that we're quite excited about. So just to continue with the summary, the psychological symptomology as captured by the clinical scores and habituation appear to be related. So that gives us confidence that there might be some common processes that might be leading to both of these kinds of phenomena. So this result of reduced habituation has implications for accounting for sensory hypersensitivities as well as obsessive interests. If you're immersed in a world where the sensory sequences you're hearing are always highly salient, they can become very aversive very quickly. So that might account for the hypersensitivity to sensory sequences. But on the flip side, if the sequences that you're observing actually have positive valence, so you like those, and you're not habituating to them, then your interest in those sequences is going to be sustained for longer than it would be sustained for a neurotypical individual. So that might account for the obsessive interest. And the findings, more broadly, are consistent with the PIA hypothesis, although I want to add, PIA is not the only explanation. So that brings me to the end of the perceptual processing bit. Let me now invite Dagmar to talk about the dynamic interception.
Thank you very much, Pawan, and thank you for the invitation, and thank you all for your interest in our work. Oh, yes. Let's begin with the people who actually do the work. Aside from talking, this is our team, and in our lab, which is now depicting my lab, which is a motion capture lab with lots of fun toys where we record motor skills and their improvement and impairments. So before starting with our specific experiments, let me just make a couple of introductory remarks. And the first one is referring back to the diagnostic criteria in the DSM-5 that Pawan already showed. And while one of the criteria is the degree of repetitive stereotypic behavior, movement coordination otherwise is not included in the diagnostic criteria, despite the observation from many caregivers and parents that motor skills are not comparable to healthy neurotypical age-matched children. There are, of course, clinical assessments that include motor skills, but these clinical assessments are known to be very coarse-grained and categorical or binary. So for a better understanding of the deficits in motor skill, clinical scales are probably not sufficient. Further, I want to point to I would say, importance of understanding better the impairments in motor skills, because if and when we have a way of quantifying these deficits, they might be a very good way of actually categorizing autistic severity, because there is no cultural or other social embedding that or language that might mediate our quantitative assessment of severity. And lastly, movement actually, as Pawan already presented, is a very good test bed of assessing the hypothesis of predictive impairment. So there is already out there a fair number of studies that have looked into prospective control anticipation, and I just want to quickly flash a list of these, where the only thing that I want to point out is, yes, there are quite a few. The red ones that I list show evidence in favor of predictive impairment, and the blue marked ones show evidence against it, or rather no evidence in favor. So the literature is mixed, but prediction has been in the discussion in motor behavior. So why? Let me elaborate how essential actually prediction is in our movements. So to first start with extrinsic prediction or dynamic interception, which is the specific paradigm that we then elaborate on. When we move in the real world, we continuously interact with objects, with our environments, with humans, with shaking hands, right? When we shake hands, we see the hand extending, predicting where and how and when we then actually make contact with the hand. Or, as we are veering towards the experiments, children interact on the playground with balls that fly to them and they need to catch. In order to catch safely and accurately, you need to predict the trajectory and the path of the ball coming towards you. And as we will see, there is anecdotal and more evidence that there is impairment. But there is more than this extrinsic prediction. There is also intrinsic prediction that is part and parcel of all the movements that we do. So this is exemplified in this diagram, but let me just summarize this briefly. We are a multi-segmented body. When I move my hands, in particular, when I move my hands quickly and the rest of my body does nothing, I perturb myself and I will fall back. In order to prevent from falling, from perturbing myself, What I, as a neurotypical, healthy individual, do is my whole trunk muscles start to contract in ways that counter the mechanical perturbation that I induce by lifting my hands. This is based on internally predicting the effects that my hand will exert onto the rest of my body, internal or intrinsic prediction. We will further, just to lay out the terminology, we will distinguish between spatial and temporal prediction. Where and when will the ball be at a certain place? And lastly, we also have a category that we refer to as post-diction. And that refers to the fact that I not only predict what is coming on towards me interacting with an object, but also what this object will do after my interaction with it, i.e., if I bounce a ball, not only do I need to intercept, but there is a target. I will have to predict how the ball will behave after my interaction. We refer to it as post-diction. So what are the problems that are out there that there is such an heterogeneous picture on the issue of prediction and several others? Well, we all know that clinical studies always have the problem of a heterogeneous population. So, as always, clinical studies suffer from the fact that there is a heterogeneous population, and ASD certainly is a heterogeneous population in symptomology as well as age and severity. There is, in this heterogeneous literature, there is also typically a multitude of tasks. People choose tasks that they have in their lab, use it, and then it is very difficult to generalize over different studies from different labs, so different motor paradigms. There is also a tendency, as I just said, using the paradigms that you already have, often developed for adults, hence you have a normative database for neurotypical adults, use it for children. And such paradigms, well, they are developed for adults and are not specifically developed for children, nor for autism. So what we try to do to overcome these weaknesses in a body of literature is to firstly have a very extensive clinical characterization using the standard scores. We eliminate neuromotor deficits that might be confounding elements, so we do a very, very diligent screening and exclusion. And we certainly match for gender, age, and IQ. The more unique element of our approach is that we have developed over the last couple of years a suite of virtual and real games where we can titrate the degree of predictive challenge in those tasks. And it's not just one task, it is a suite of tasks. And it is both naturalistic and virtual tasks, so that, well, virtual have the advantage of being very precise. However, well, virtual is not real. Does it translate into the real? So we embrace both. Well, and lastly, we had a lot of fun designing these experiments that we make them appealing to children, and I hope you will like them too. One more preamble before this suite of experiments is the anecdote is from parents and others that I, or children with autism, can throw but cannot catch. Well, throwing is just getting rid of a ball in a targeted way, but nevertheless rid of a ball, whereas catching has the element of prediction that I just explained earlier. So we did a first set of tests using a experimental setup where the children just threw a ball in a virtual environment. And as the two bars summarize, black neurotypical children and ASD in red, that their percent success in hitting a target does not differ. This contrasts with another experiment where we just looked at children catching a ball that was launched from a ping pong ball machine, and they caught it either two-handed typically, and we looked at the same a neurotypical and ASD, and you see a large discrepancy in the degree of success. So a very first relatively broad experiment was very much consistent with the anecdotal reports that we heard. So how did we then continue? Here is our experiments. We start to test intrinsic prediction with realistic catching. We then go all the way down to reducing the motor element to just key presses and have two different tasks for spatial and temporal prediction. And then we have 3 more tasks where the interaction with the environment is with a handheld paddle, where we measure the displacement of the paddle in interaction with the virtual object. And we can test prediction and interception, pre- and post-diction. And lastly, as a control task, reaction time in the same setting to account for, well, alternative causes for motor impairment. So let's begin here with our very realistic catching. As you can see, our child stands on a force plate and a ball gets launched towards them from a covered up ping pong machine with that star where they have to gaze at the star to guide their attention. And balls come with 2 different speeds and they catch. We measure extensively the movements of the children with motion camera, where we have markers on the body to have joint angle movements. And we have force plate to look at sway of change of body, as well as EMG sensors that measure muscle activity in the trunk, front and back. So how do the results look like? Let's first just look at the hand and the ball. And one measure of how the hand intercepts and approaches the ball is looking at the distance between the ball and the hand prior to catch, and in fact at the velocity, how that distance changes, which is this slope that you see over time prior to the moment of catch. And for NT subjects here, this is a relatively constant slope, whereas here, this means that the approach velocity increases prior to catch, which is a good sign for a collision. Summarizing on the side shows that the slope is much higher in the red bar, ASD versus NT, so this exemplary data is truly representing the population results. Then here, some exemplary data from EMG, from muscle activity. Here, the NT child showing 4 different muscles, front and back. And the vertical line here is the moment of catch, and you can see some elevated activity, approximately 400 milliseconds prior to catch, and then relatively low-level controlled activity. For the ASD children, the muscle activity increases in an almost synchronized fashion with a maximum at contact, meaning at the collision, the body is contracting. There is no predictive activation of the muscles prior. So again, we looked at one muscle and we did some statistics that this actually held over a number of different subjects. Moving on, of course, whole body tasks, a lot of things can go wrong. So let's look at some elements of this task, and the one is postural stability. We look at force plate data, which just look at the projection of the center of mass onto the ground. And very typical behavior is, as you see above in these, I call them spaghetti plots, that there is sway, more sway when you're blindfolded versus eyes open. Left and right is one exemplary neurotypical in black and an autistic child in red, and there is no difference. That is shown again in the population data that we have. Neurotypical in gray, eyes open, blindfolded. Yes, there is an increase, but the increase is very parallel in the ASD children, meaning there is no difference in postural control without the added catching movement. Another element here is just reaching out and reaching to a static ball where we look at reaction time. There is a verbal a metronome cue, and at peak velocity. And these minor differences between the two bars, they're not significant, meaning catching a stationary ball, both populations do similarly well. So this helps us to isolate that the problems that are very visible in the real catching task are not due to some of the elementary components, but rather to the predictive element. So moving on, here is our first task. Ball is long on the left, is occluded by the house, and then our subjects have 3 buttons of the same color as these 3 different mice. And the question is, which mouse gets the ball, or the cheese actually? And the results look as follows. In black, as before, neurotypical versus ASD for the top mouse, the middle mouse, and the blue mouse here. And while there is no difference for the top middle mouse, the difference shows up with the bottom mouse in their ability to perform. And why? Because if you look at the trajectory of the yellow ball or cheese here, and then how it shows up before and behind the house, you can see the discrepancy of the blue trajectory just following ballistic flight is largest, meaning this is the most challenging mouse to predict, and this is where the difference between neurotypical and autistic children starts to show up. For the same experiment, we also looked at the gaze trajectory, stimulated, motivated by Pawan's earlier work on the Pong game. And subject wore an eye tracker, and here on the right is time, and this is the trajectory of the cheese or ball, which has a linear velocity over a linear change in the x direction over time. And the gaze of a neurotypical child is following, kind of after a while, following the ball, even when it is occluded by the house. This is basically the house flipped over because we look at the x direction. Now, the autistic children also has a delayed start, follows the ball, but when the ball disappears, the gaze stagnates. There is no prediction of how the ball would continue behind the occluded house. So very much in line with what you saw by example from the Pong game. An inability to predict the ball's trajectory. The next game is temporal prediction. So here, now the subjects have to predict when the ball appears in the house with a cross. So it is temporal prediction after a ball is occluded. Here, the results looked at as follows. We had 2 ball speeds, fast and slow, and the results show that the neurotypical one have a timing error that is much larger in the slow than the fast one. And this scaling of the temporal error with time is a very common observation in all kind of temporal judgment and estimation tasks. The autistic children are similarly, call it bad or not so good in both slow and fast with a relatively high variability. So they do not show the typical error pattern in time estimation as is usually seen. Extrinsic prediction, and now our children hold that paddle and a ball is and they have to catch it after it is occluded by the tree. And the 3 stars mean that they catch the ball very accurately where the ball hits the paddle or the basket in that red dot in the middle, in the center. So we can have an error measure as well where the ball actually hits the basket. Experimental manipulation, we enhance the predictive challenge by adding 1, 2, or 3 trees. 3 trees is the most difficult to predict because the occlusion is relatively large. So here are the data. For 1 tree, neurotypical and ASD perform equally well. For 2, there is a difference starting, and for 3, where the predictive challenge is very high, the difference starts to emerge and become statistically significant. One more. Post-diction. So the same paddle they hold is now used to bounce a ball into the crocodile's mouth. So they have to predict the ball as well as post-dict. They have to control the velocity of contact, the right release velocity to hit the crocodile's mouth, where 0 error is the tip of the tongue. Results are here. We have a target error, which means how exactly do they hit the center of the crocodile's mouth. And neurotypical children have lower error than ASD children. And if we just look at the standard deviations over batches of trials, their variability is lower or higher in ASD. And particularly the variability, we have methods to further examine distributional properties of variability with respect to the known parameters. Without going into details right now, this unfolds the pattern of variability even further to give us a bit more insight where the impairment comes from. Now, as before, also for the virtual tasks, we have a control task because one essential component in motor skills is reaction, right? So we created a control that you see right here, where whenever the mouse appears, that's the reaction time signal that they have to catch the mouse as fast as possible. Because if they're too slow, cheese on the side disappears, and we don't want the cheese to disappear. So that is a very nice motivation for the children to be as fast as possible. Here, the results are very nice and interesting. Reaction time in ASD and NT children does not differ. Mind you, this is different from several reports in the literature. The only way that I can understand this is that in our task, children are very engaged. And actually, there is some sound in the back that didn't play right now, but there is additional sound effects and rewards, and the children really like it. They're engaged, and therefore, I would say they show their best performance, and reaction time certainly doesn't differ from ASD to NT in our experiments. Okay, so this was our suite of experiments that sort of engage the children and titrate and measure their predictive abilities. And, well, I think we are accumulating supportive data that indeed the predictive element is what seems to cause the less good performance in ASD. Now, we're still in the middle of doing that, but on the side, we had one other interesting project that created a whole bunch of, call it, normative data. In order to test the validity and engagement and all of that of our suite of experiments, we took the opportunity at the Museum of Science in Boston to do for 1 year data collection, which also was an outreach activity to tell the public what we are doing and inviting them to participate. So we collected up to, more than 400 healthy people at all ages in a very reduced experiment because we weren't allowed to engage them for longer than 15 minutes. And they played all of our games, and the curves and success rates that we observed in all those games gave us a very nice, call it a tapestry of neurotypical performance. And we certainly saw patterns, meaning even when played in a very uncontrolled noisy, engaging environment, they were still sensitive to extract some scaling in the respective quantities. The final thing, or rather the now starting thing, is that we take these very games and we put them on the internet, and we want to deliver them to the Spark database to now get a larger sample of data that test our predictive impairment hypothesis. And I conclude here and pass back on to Pawan.
Well, so Dagmar, I think that's yours. So, well, this is a summary of what Dagmar said. So in physical as well as virtual settings, children with ASD exhibit reduced performance relative to NTs as predictive requirements for interception are increased. And as her control data shows, these impairments are unlikely to arise just from a generalized slowing of responses. The last little bit is that on probabilistic reasoning, and I'm very quickly going to flip through the slides, even though Nushin would be the person to really do justice with this material, but just to give you a flavor of the kind of studies we are doing there. So the question we started out here was, how can we probe the neural mechanisms for and performance on probabilistic learning in ASD using a task that's largely devoid of social aspects? And the answer to that question that we are using is the weather prediction task. So this is a task that has been devised by Knowlton and colleagues. As you see in this animation on the right, the task involves showing the participant a bunch of cards, 2, 3, or 4 cards with different patterns printed on them. After they have seen these cards, you ask the participant, does this mean that tomorrow, figuratively, is going to be sunny or rainy? And that's why the name weather prediction. So initially, of course, this doesn't make sense. Children are performing at chance. But as this goes on, because there are systematic relationships between the individual cards and how much they predict sunniness or raininess, eventually the participants come to internalize those kinds of linkages, and their performance gets to be above chance. So this task has been successfully used with other clinical populations. It's non-social, and it combines multiple cues per trial. So it's not just the linkage between one entity and another entity, but multiple entities, which is more reflective of what you would see in the real world. So the behavioral results that we have so far seem to be pointing in interesting directions. So what you're seeing here are blocks of experimentation. So think of this as a proxy of time. And on the y-axis, you're looking at the percent correct performance. So neurotypicals asymptote around at about 70% correct performance. ASD individuals, however, asymptote around a little around 55 or 56%. And that's shown in the bar plot on the right. To complement the behavioral studies, we decided to also conduct neuroimaging because we're interested in using this task to get at what might be the neural substrates involved in prediction. So we used fMRI at MIT, and we had 2 versions of the task, so we could compare one against the other. The first version, which we call the probabilistic task, that's the conventional weather prediction task, as I've just described it. The control condition is the deterministic condition, where the subject is not being asked to make an uncertain decision. Rather, they're simply being asked to report what are the patterns printed on a given card. So you notice on all of the cards you see sunny patterns, and hence the response has to be sunny. If you were to see clouds on all of the cards, the response would be clouds. So it's a completely deterministic response that they have to provide. So the children did this task in the scanner, and we are looking at the patterns of brain activation when they're doing the probabilistic task versus the deterministic task. Here it is for neurotypicals, here it is for ASTs. If you subtract one from the other, so you look at which regions of the brain are responding more to the probabilistic task relative to the deterministic task in the AST population and in the NT population, you see some interesting differences. There are very few regions that differ across these conditions in AST, but many more in the neurotypical brain. So cortical activation for probabilistic and deterministic conditions is similar in AST, and in contrast to NTs, there's no basal ganglia activation in AST for the WPT. And basal ganglia are an interesting structure in this context because other studies have implicated them in predictive tasks. But this is a story that's still developing. The initial results seem to be quite interesting. So just to summarize, participants with AST show reduced performance on the weather prediction task. As they learn the task, so these are data that I didn't show you, as they learn the task, AST participants find it difficult to report how predictive is a given card for sunniness or raininess, whereas neurotypical subjects can quite readily describe which of these 4 cards is most predictive of sun or rain. And the fMRI results indicate that some key neural regions implicated in prediction, like the basal ganglia, are not differentially activated in probabilistic versus deterministic tasks in AST individuals. So to conclude, we've talked about our baby steps towards empirically testing this idea of a predictive impairment in autism. We've looked at these domains of perceptual processing, dynamic interception, and probabilistic reasoning. And on all of these fronts, the story is not completed yet. We are still working. But even as we are fleshing out these threads, there are some interesting new avenues that we are considering. One of them is this. This is simulated driving. So it's interesting that high-functioning autistic individuals who certainly have the IQ to engage in very complex tasks, very few of them drive. So according to the National Transportation Center, less than 20% of high-functioning autistic individuals drive. And the obvious question is, why do they find driving difficult? What aspect of driving is difficult? So looking at it from the lens of PIA, we would like to probe whether there are telltale differences in the predictive behavior that a driver engages in during driving between the AST group and the NT group. In collaboration with the Technical University of Munich, that has the world's best driving simulator. They spent about $5 million on that simulator. We are trying to get at that question. So the bottom line that I had started out with, the results so far, I hope you agree with us, are encouraging, but a lot more needs to happen before we can have more confidence to reject or accept PIA. One other thing that has encouraged us about the predictive impairment hypothesis is that this paper has been read not just by scientists, but by the public at large. And we've received many notes from parents, and here's one example, which suggests that maybe there's a grain of truth to this general idea of a predictive challenge. And I lay great store in these comments for a person who has observed this condition up close 24/7 for years on end. For them to see the validity of an idea, I think that's a great booster of confidence. And I hope that this outreach to families that are affected by autism, and this crosstalk between science and the public at large will continue further, and we'll be able to contribute to that conversation. And with that, I would like to thank the Simons Foundation and all of the wonderful collaborators who have made this work possible. Thank you.